Okay, welcome to lecture 25, the final lecture for this stats class. So today we're talking about correlation. So the idea is we were talking about scatter plots last time and best fit lines. So the idea is you want to know the relationship between two kinds of data. So if one goes up, does the other go up as well? Or maybe the other one goes down. So do they sort of interact and move together? And the idea behind correlation is how much they're related. That's the idea. We want to measure how related things are. So it's not just a yes or no question that they're related or not, but how related are they? Okay. So let's think about the two scatter plots I'm about to draw. And we'll just sort of compare them. So I'm trying to draw them in a very specific way to hint at something. Okay, so here's the first one. Okay, so there's the data, it's very line-ish. So if I draw the best fit line, it's sort of gonna go right through the middle there, nicely. And all the points are pretty close to the line, which is good. And so that's telling us we should think of it as the two types of data, whatever they happen to be. So your X data and your Y data. Oops, there's no margin there, so I can't write. Your X data and your Y data are very related. So as X moves to the right, as X goes up, the Y goes up proportionally in a very nice way. Versus another scatter plot where it's still very line-ish, seemingly, but the data is sort of a bit more spread out from the line. So I tried to exaggerate it. I would have liked to exaggerate it more, but it's hard to draw. So the data points are further from the best fit line. And so what we want to do is we want to somehow think about this first one as being better. So, but in a very statsy way. So that's what we're going to say next. Okay. So I try to draw them in this way, but they're supposed to have roughly the same best fit line. That's what I was trying to draw, at least. I was trying to make sure they have the exact same line. But how are they different? The points in the first scatter plot are closer to the line. So the line is a better fit than it is in the other situation. And so we want to talk about what that means. So what does it mean when your line is a better representation of your data? So what we say is that the data in the first plot has a stronger, we use the word stronger, statistical relationship. And then the fancy word for statistical relationship, EIE, is correlation. Than in the second plot. So when we think about correlation, we're just going to be thinking about a stronger relationship. And so in these scatter plots, what that means is that the line is better it's more line-ish. The more line-ish it is, the more the two data are strongly related to each other. And then this measurement of how good of a line it is can be measured with a number called the correlation coefficient. So the correlation coefficient, so don't worry, you're not going to have to calculate this in this class. If you go further in another class, you probably will. The correlation coefficient is always called R, is a number that reflects this concept for a set of data. So some properties are that it's always between -1 and 1. But the closer to 1 or -1 it is, the better, the more closely the two data types are related. So, but in two different ways. So if R is close to 1, then this indicates a strong positive correlation. So what that really means is as X increases, Y increases, and in a proportional way. So a situation in which this happens would be something where the data looks like it's forming a line that's going up. So I'll just draw some random points here, but something like this would have R very close to 1. And the best fit line is very close to all the points. So you can try to draw it, I don't know, just do your best to look something like that. But in any case, so as X is going up, so as your X data point is increasing, there's a pattern where your Y is increasing around the same amount proportionally as you go over and up. And so that's going to tell us that our R is close to 1. And so what we say is it's a strong positive correlation. The other thing that can happen is R can be close to -1. So it can go between 1 and -1. But if it's closer to -1, then this is sort of still good in a different way. This indicates a strong but negative correlation. So really this just means that as X increases, Y decreases. So the idea is that they're still affecting each other, the numbers at least, maybe not the actual things, but the numbers they move together, but now Y is going down as X is going over. And so a scatter plot like this, where as you go over to the right, the points are going down in a proportional way, forming a line, or something very close to a line, gives you a value of R that's close to -1. And the best fit line, again, reflects that because it's going to be close to all the points, but it'll have a negative slope. It's going down. So just to remark that, the best fit line is close to all the points, and it will have a negative slope. So that's your y equals mx plus b formula. This number here will be negative. It doesn't have to be close to -1 or anything. So don't get mixed up between r and the slope. Two different things that are a little bit related. But don't try to like intertwine them too much. It might get a bit confusing if you do that. Okay, so now let's see one more type of example. So what if r is not close to 1 and not close to -1? Well, then it must be closer to 0. So what happened? What would that look like? Well, that would mean that there's not a very strong correlation, either positive or negative. And so that would mean that the data points are sort of not forming a line, but maybe they're doing something else, and something like this. So they're not really line-ish at this point. So something like this will have r close to 0. Or at least not close to 1 or -1. The best fit line is not really close to all the points. So there is still a best fit line. You could still draw a line where you try to minimize the total distances, and maybe you'll draw, I don't know, something like that. But it's very far away from a bunch of stuff. So these distances are all pretty big. So that's just saying that r will definitely be closer to 0 because it's not very line-ish. So the two data types are not really linearly related at all. They don't have a strong relationship to each other. Okay, so let's do an example where we look at some actual data. Those are all just sort of some random examples without any meaning. So now let's try to do some context. Okay, so scuba diving, very relevant context for all you kids, because everyone does this. Scuba divers have maximum dive times, so how long they can stay underwater, that they cannot exceed when going to different depths. So the idea here is that there's a relationship between the amount of time a scuba diver can be underwater and the depth that they go. So because there's a physical relationship, there should be a statistical relationship. There should be a relationship between these two data types, these two sets of data. And so we should have a correlation, R, that's either close to 1 or close to -1. So let's see if that happens here. So here is some data that's maybe somebody has collected or something. So on the X will be depth, and I don't know why I did Y as time, but I guess I did. Time will be Y. Usually people like to put time on the X-axis. Okay, so, but I guess it's the way this is worded. So the time is dependent on the depth. So that's why people like to put the dependent thing, the one that's dependent on the other, as the Y. So that's one reason for making time be Y in this situation, when usually it's not. Okay, in any case, so here's the data. So 50, 60, 70, 80, 90, 100. So I guess these are in meters, or no, these are in feet. Units don't matter too much for us. And this time will be in minutes. Okay, so the idea is that the deeper you go, the less time you can be down there. So this is going to go down in numbers. So 80, 55, 45, 35, 25, 22. Okay, so just we're going to treat this sort of like as a quiz problem. We're going to make a scatter plot. And then we're going to estimate the best fit line. So this is stuff we did last time. And then we're going to, let's see, we're going to make predictions. So given a best fit line, so this is still stuff we did last time. So notice that the m, the slope of the line, is negative already. So if this is the best fit line, guess the dive time for 110 minutes. Okay, and then we're going to determine, so this is the new stuff, but it's really not much that we have to actually do, determine the correlation. So we're not going to actually calculate R because R is very hard to calculate. You need a fancy calculator, or you need to learn a lot more math before you can do that. So we're just going to determine the correlation using the scatter plot. So we're just going to say if it's strong or weak, and then we're going to say if it's positive or negative. So strong and weak, that's just saying it's either close to 1 or -1, that's strong. And then weak is closer to 0, or not close to 1 or -1. Positive or negative, that's just is R positive or negative, is the line going up or down as it goes to the right. Okay. And then I'll ask one more question after all this. Okay, so let's do all this first. All right, so let's make the scatter plot. First step. So the x-axis is depth. I got to label the axes. And the y-axis is time. And this is nice. It just counts by 10, so I can just do that. 50, 60, 70, 80, 90, 100. And then time goes from 22 to 80. So maybe I'll just go 20, 40, 60, 80. Okay, so now I'll plot these points. So 50, 80, way up there. 60, 55 would be about there. 70, 45. 80, whoops, I skipped, sorry. 70, 45. This is why you don't graph in front of people. You just show the end product. Whoops, make small mistakes. How embarrassing. Okay, 70, 45. That's okay though. 80, 35. There's no mistakes. It's just fun accidents that you can learn from. 90, 25. And 122. Okay, so something like this is the scatter plot. Estimate the best fit line. So it's the line that's trying its best to minimize total distances away from all the points. So that seems pretty good. So now this is the actual equation of the line. So we're going to estimate what would happen at 110 by figuring out what that point is by plugging in a depth of 110, into a calculator, of course, I'm not going to do this by hand, but I plug this into the line as the x value and I get the y value, it'll turn out to be, let's see, did I not do this? Yes, I did. Okay, 4.678. So this sort of reveals the flaws of this approach. So this is a very simple approach, and it's a bit flawed because if you notice, if you sort of look really closely at these numbers, the time is not going down by very much as you continue. So if I had to just guess, I would think it wouldn't jump all the way down to 4. But because I'm using a best fit line, it's forced into modeling how the two data are related with a line, even though they might not be linearly related. So this seems like it's not linearly related because up here it's sort of shrinking faster. So from 80 to 55 is a big jump. Then it only jumps by 10 a couple times, and then it jumps only by 3. So you don't have to worry about this stuff too much right now. I'm just trying to point out that you can't just assume everything is linearly related and works perfectly. But 4 is what you'll get if you do this. So that's going to be the answer for this, 4.678. Okay. So if you take more stats classes, you'll learn much fancier things to do this better. Okay, so what about number 4? So does the best fit line seem very close to everything? To me, it does. So the best fit line is close to the data. So I would say it's strongly correlated. And if you wanted to put this in context, you would say, so as the depth increases, well, is it strongly correlated in a positive way or in a negative way? In a negative way, so I should have said that here. Strongly negatively correlated, or strong negative correlation, however you want to say it. But the point is that as the depth increases to the right, the time decreases, it goes down. So these are negatively correlated, and because the line is pretty close to the points, it's a strong correlation. And they do so proportionally. Okay, so that answers number 4. It's a little more than number 4 asked for, but that's okay. Okay, so now I'll add on one more question. So now pretend that I give you the actual correlation, and does it go with what we answered with number 4? So does the actual correlation coefficient, so again, you're not going to need to calculate this. I'll just give it to you like this. Negative 0.9629. Does this, being the correlation coefficient, support your answer for 4? So the answer here is yes, because we said it was a strong correlation and it was negative. And the answer is yes, because it's close to -1. And that's exactly what it means to be strong and negative. So yeah, if it was like 0.5 or something, negative 0.5, then no, because that's not very strong. Okay, so now let's go back to another example. So you're gonna have to look in your notes for this one because I don't have it rewritten down here. But let's go back and look at your notes from last time. Consider the exam example. So that was the one that had first exams as the X and second exam, or sorry, no, final exam. Now, my drawing, if I recall, was pretty crappy. And I tried to make a best fit line. But if you really looked at it, it wasn't very line looking at all. And in fact, if you use a correlation coefficient calculator, so you can Google that and very easily find one where you just type in the data. So it turns out that for that example, R is 0.6631. So, in fact, the correlation is very weak, is what we're going to say. So the correlation between the first exam and the final exam is weak. You could say it a couple different ways. I'll say weakly positive because it's still a positive number. So as as the first exams go up, go to the right, the final exams do go up, but not in a nice proportional way that the line fits all the data. And so that's why this number is not close to 1. So that's where the weak comes from. Okay. So then one last thing I want to just mention is this quote that people love to say. So correlation does not imply causation. So what this means is that you can have R close to 1, but the two data go up together proportionally, so that's all good and well. So let me say it like this. R close to 1, so the data goes up together proportionally, but it could just be completely coincidental. Meaning that the X going up is not actually causing, that's the word causation, it's not actually causing the Y to go up. They just both happen to be going up at the same rate. So if you Google around this phrase, you'll see lots of examples of things like this. Maybe I'll put some examples in the lecture problems. But then people also misuse this phrase too much to try to discount when people do find correlation and try to talk about causation. So what can happen is you can have strong correlation, and what that means is you should investigate if there is causation for some actual reason. And sometimes if people don't like the results, they just use this phrase to say, oh, it doesn't count, even though they didn't actually read the research to see how the person established causation after they established correlation. But in any case, if you need to learn that much stats in the future, then you'll know all about that at that time. Okay, so that's the end of this and the final lecture. So have a nice life, I guess. Don't forget to like and subscribe.